Next presentation is going to be by DeWayne Wilson. Mr. Wilson's a licensed professional engineer in Washington State and has been with the Washington State DOT for nearly 34 years. He is currently the bridge asset engineer and is responsible to establish and prioritize the statewide bridge preservation needs.
My presentation today is kind of like an owner's perspective of bridge deck preservation. So if you've never been to Washington State before, it's kind of a beautiful state, a diverse state. It has two distinct areas. There's Western Washington and then there's Eastern Washington, kind of divided by the Cascade Mountains. Through the Cascade Mountains, we have three highways that run anywhere from 3,000 to 4,000 feet elevation. So the western side of our state gets a lot of rain, not as much snow. The eastern side of our state gets a lot more snow and it's hotter and colder. So throughout the state, we do have de-icers that we're using, and we are using plows up in the mountain passes and mostly in eastern Washington during the winter time. Some notables as far as on the western side, you might recognize some of these companies that are headquartered in Washington: Microsoft, Costco, Amazon, Starbucks, PACCAR, Weyerhaeuser. Then on the eastern side, we have a lot of agriculture, a lot of crops. We lead the nation in apples, cherries, asparagus, mint, hops. So what this means is our state relies a lot on trade. Our state relies a lot on our road and bridge network. And that's where bridge preservation comes in. We need to preserve our bridges in order to get our products and our industry to the ports and delivered. Also for tourism, for people visiting the states when they come see our state. So here's just kind of a map of, it shows a breakout, couple graphs here. We have about 3,120 bridges on the state system, 53 million square feet. Replacement value about 58 billion, average age 48. I did a little graph there. Most of our concrete decks are cast in place. We have a small population of bridges where we drive directly on a bridge beam or girder, and so the deck is integral with the beam. Now if you take that graph cast in place, the type of bridge, half of those are integral with the bridge and half are non-integral, and I'll talk about that in a minute. The superstructure types, we're traditionally a concrete state, so about 3/4 of our bridges are concrete, about a quarter, less than a quarter is steel, and then one little sliver there still we have some timber bridges. So if you look at our concrete bridge decks and the condition, I kind of call this the condition donut. So the way that we categorize our condition, good, fair, poor, I'll explain that in a minute. But so we have about 58% in good condition, 38% fair, and then this sliver about 4% in poor condition. That represents about half of all the bridges on the state highway that are in poor condition. So what that means is, you know, one of the major reasons a bridge is in poor condition in Washington State is because of the deck. So here's that interesting detail that kind of gets overlooked, but as we're preserving our bridge decks, thinking about the treatments, thinking about how to do it, we need to know what kind of design we have. So we have a variety of bridge decks that have non-integral decks. Basically, you could take that deck off and the bridge would still be standing. So we have a variety of steel and pre-stress and other bridges, concrete arches that have these non-integral decks. They're pretty easy to work on because you don't have to worry too much about how much of the deck you remove. But the integral decks are the ones that you have to be careful with, the slabs, the boxes, the beams. We are famous for floating bridges. 4 out of the 5 biggest floating bridges are in Washington State, and the world's biggest one is in Washington State. So again, those type of bridges, the segmental post-tension boxes, and then also the beams that we drive directly on. These are really interesting when they start to deteriorate and you go in to do some type of treatment. The designers need to think about the load pass and how much of the deck you can remove. So any type of typical concrete bridge deck, you'll have these type of issues, either just straight out deterioration from chlorides and rebar corrosion to rutting, rebar cover issues, and then poor quality concrete. So when it comes into just normal deterioration, we've had lots of presentations here on how the chlorides get into the concrete, cause deterioration, the rebar corrodes, cracks, and then finally you'll get some breakouts. And so here's a deck where they've done a chain drag survey. They've marked out some of the delaminated areas, and those black spots are where they temporarily patched this deck with asphalt, which I didn't like. But so this is kind of what you would see on some of our previous decks. And then here's the next generation as we're getting into it. I'll talk about this in a minute as far as the root cause, but we're experiencing a lot of rutting in our bridge decks, especially in eastern Washington. So this little scale here shows that this bridge deck had 1.5 inch ruts. The backstory is this was about a 30-year-old microsilica concrete, 10,000 psi, so after 30 years in this environment, it's got 1.5 inch ruts. So what the maintenance crews did, they came in with some polymers to kind of treat the ruts temporarily until we decide what to do, either full replacement or a rut repair. Here's an overview of what they did. In some cases, they went full lane width. Other cases, they just went down to wheel line. So here's the big offender is studded tires. And so a lot of the northern states and a lot of states with snow, they have studded tires, and that's Washington too. This is kind of the enemy of any state bridge owner. We know what the studded tires do over time, but trying to convince the culture and the environment that studded tires is bad is kind of a hard lift. It's a hard push. It's an emotional issue. Everybody wants their studded tires, thinking, that's what's going to do it in the winter times. But there are a few states, Minnesota, Mississippi, Wisconsin, and kind of a no-brainer, Hawaii, don't allow studded tires. So if you can find the recipe of how they got studded tires, outlawed, that'd be a great recipe to learn. So here's another bridge deck where the rebar was built kind of shallow, and then over time it's been exposed. Here's a bridge deck that just had poor quality concrete, but the bridge itself did pretty good because it lasted about 75 years before the concrete just said, hey, I have enough. And so we eventually had to replace the deck on this bridge. So let's talk about what we do in Washington State as far as evaluating and inspecting bridge decks. We kind of differ from the national core elements on the BMS. So we've designed some agency elements. So we have unique overlay elements for modified concrete, polyester, asphalt overlays. And then we'll have different deck elements for either decks with just black steel, decks with epoxy coated steel. And then we will have a different element for looking underneath the deck on the soffit. So kind of how this works is it's kind of different. You would normally look at the different condition states from going from good, fair, poor, but we don't do it that way. We kind of look at condition state 1 as being good. Condition state 2 is how much the deck surface has a patch in it. We want to know that. Condition state 3 is anything that has a spall that hasn't patched. And we use condition state 4 as kind of a placeholder for any delamination results. So down below you can kind of see this with this particular deck we have over 1,000 square feet of patching. So that's parked in condition state 2. What that allows us to do is then we know that this deck has 26% patching. So what we've done is correlated the NBI to these percentage patches and then came up with this rating so that we can be uniform. All inspectors know how to rate based on NBI and the BMS, and then how we can use this in asset management to deliver a plan, a preservation plan. So as you go down the NBI scale, if you have no patching, then you get to a 7. If you have any patches up to 1%, that would be a 6. 1 to 2% would be a 5. 2% and above to 5% would be a 4, and then anything above 5% is a 3. So that previous deck I showed had 26%. We came back in, we did a hydromill, a concrete overlay. So when the inspectors go back out there and look at it, they reset all those condition states again. So you'd see nothing in condition state 2, 3, and 4. So this is rated an NBI 7. There's kind of a weird thing where, it could be an 8. but there's always a little conservatism in inspection, so they drop it down to a 7. So here's a deterioration curve that we can use, and we can back this up with a massive amount of data. But basically, as we go along, the deck is okay, but then once you start seeing some patches, some deterioration, at 1%, that's where you start that curve and that decline. And so then there's a time element that we can figure out too. We've figured out that at the 1% mark, we want to program that over the next 10 years. At the 2% mark, that's when we start calling it poor condition, and then we can prioritize those. Anywhere from 2 to 5% is that kind of that sweet spot of where it should get repaired, but we're kind of, due to funding, lack of funding, we're kind of exceeding that in a lot of cases now, and we're going past that into the 5% range. Also, if maintenance goes out there and patches up to 2%, we kind of think, hey, you've done your job, now it's time for a capital project to come in, do a preservation activity, because we just don't want them out there all the time patching this deck all the way up to 5%. So we do an annual report, and it might be a little bit hard to see, but basically what we do is we look at those, and we kind of parallel what they do in highways. So we say what bridges are past due, what bridges have more than 5% patching on them, we call that past due. What bridges are due for repair, anywhere from 2 to 5%, and then what bridges should be done over the next 10 years based on that deterioration curve, and that's anything with the 1 to 2% patching. So when you do that, you add up the numbers, you calculate how much it costs. Our total need is about $868 million over the next 10 years, but our funding is only 150. So basically we have a gap of about $72 million per year. There's going to be some consequences to pay because you reap what you sow. If you don't preserve your bridge decks, eventually you're going to have to replace it at 3 times the cost. So kind of like a graphic of that, we have this map. You can't really see it, but there's little orange dots that show all the bridges in poor condition. These big red dots are the ones that are due to deck condition. And you can see a cluster of ones kind of in the center part of that map there. That's along I-90 going up towards the mountain. That's a main freight route. So we're prioritizing those higher, and based on the lack of funding, we're concentrating on the main freight routes right now. So this is what you'll see if you come to Washington in the summertime, is you'll see the orange cones and the maintenance crews out there patching decks. These are the unsung heroes that are kind of keeping things together, band-aiding things together. But it's not economically, it's not a good model because the numbers just don't work out. If they start patching more than 2%, it just doesn't work out. You would be well ahead to do a capital project and do a preservation. We know that. We're just waiting for the funds to help us out. So here's another picture. Another region likes to use the urethane-based patching materials. So this is kind of a urethane-based material. Looks kind of ugly on this particular bridge up on the mountain pass. Then here's another bridge heading up towards the mountain pass. It has kind of little spot areas. But, you know, in a constrained budget area, this is the new normal. So I'm going to kind of use this graph to kind of guide us on different overlay types and different deck types. So nearly half of our bridges have overlays on them. The other half don't. And then if you split that in half, about 29% have epoxy coated rebar, and then about 20% has just normal black steel. So kind of the year prior to 1980 is when the bridges had black steel, and then after 1980 we put epoxy coated rebar. So as far as those bare decks with just normal steel in them, we've got about 589 of those bridges. Average age is 53, oldest is 95. So this is, really hard when they talk about, deterioration rates of a normal deck, needing to replace a deck at 40 years. We just don't see that in our state. So we have this data that kind of backs it up. So most of the condition of the decks are in, good or fair condition, with about 11, 12% in poor condition. So this particular bridge, 95 years old, concrete arch, they built it with a 10-inch thick deck. It's performing well. It's had salt all its life on it, but very little patching is done on the bridge. So, could it last another 10 years? Probably. And so this next bar is for all those bridges with epoxy-coated rebar. We started using epoxy-coated rebar, generally as a practice after 1980. We did some experimentals prior to that. So this graph just kind of shows you a little bit of the history. It was kind of interesting because the first generation of epoxies were actually black. Then they turned to brown, and then I don't know what the thought pattern was to turn to green, but at least you can see it on your bridge deck. And so from about 1980 to 2007, we did the top mat only. And then in 2007 forward, we decided to epoxy coat both mats. So if you look at the condition donut, most of them are in good condition. Small population, about 17%, are in fair condition, which means they have some level of patching done on them. Here's one of our oldest ones. This one had epoxy coating put in by change order in late 70s, 1979. It's pre-stressed girder bridge, 7-inch deck, 2 inches of cover. It did have a lot of cracking on it, so the chlorides are getting down into the rebar through the cracking, and now we're starting to see it has about 1% patching on it. So it's on that path for needing some type of preservation action. Here's a newer bridge in a region in a town called Bremerton, which is a Navy town. We built this new bridge to cross the Puget Sound from one side of the town to the other. Pretty good looking bridge. It's a pre-stressed girder. It has some unique details where we wanted to make it look somewhat like an arch. So the thickness of the pre-stressed girder it varied a little bit. And then we do have about a 250-foot main span. We have a drop-in pre-stressed girder, post-tensions. But the one negative thing about the bridge, when you look underneath, it does have a lot of cracking. And so what we saw was a lot of our decks built in the 2000s, for whatever reason, experienced a lot of cracking. Typically, we would see a crack about on every 2-foot center. This one just had cracks of like every 6 inches. And so here's the top side, and the cracks were there too. So Chris Keegan in our Olympic region asked a couple companies to come out and demonstrate some crack sealing products. So they did a little trial section for us, and we would like to go ahead and crack seal the rest of the bridge, and we figured that would cost about $200,000. So when it comes to brand new bridges, we did this little research project to say, hey, what's wrong with our recipe mix? What we've traditionally done for a long time, what's wrong? So we had a university look at it. They looked at all of the qualities of concrete, said everything looks good, but it cracks. And we said, okay, well, thanks for that information. And so, so then we got together with our construction office, and then we decided, well, maybe we should change. Maybe we shouldn't go for a recipe mix. Maybe we should do a performance mix. What this means is you identify which performance you want in a bridge deck, and then you target those performances, and then let the contractor and the concrete supplier meet those criteria. Then you have a performance mix. So that's what we did, and since 2013, we have about 88 bridges built with that performance mix. And so far, it's doing pretty good. We did another report in 2015 where we went out and actually looked at those bridges, documented the information. We were a little creative. The designer and the person doing the research report looked at how much crack was in each bridge and did a percentage thing. So if you Google or look up on our website these different WARD reports, you'll kind of see the methodology they use to identify the cracks. So in the different mixes, we had a traditional recipe mix, 4,000 PSI, all these constituents. We called out for quite a bit of cementitious paste. So at one time we had 660 pounds of regular cement, but then we said, okay, we're going to add some fly ash on top of that. Well, we didn't take away any cement, so that was quite a bit, 735 pounds. So now we don't set any limits at all. We just say whatever cement you need to meet certain criteria, put that in. Traditionally, they backed it off to about 565 to 610 pounds in their mixed designs. So we don't require any pozzolans. We do require a gradation of aggregate 1.5 inches minus. And then next one, air content. We require that air content 4.5 to 7.5. We have a criteria for freeze thaw, permeability, and then this shrinkage is the key there, is we set a limit at 320 microstrains, per AASHTO T160 test. And so we thought, this is the kicker when you do a performance mix, because you go out there with a contract, and then for the permeability and this test, it takes them about 30 days to do this, but they could be doing that while they're building the bridge if they're proactive. So it didn't seem to harm us at all. And then the one other key is the admixture. The shrinkage reducing admixture is common in all the performance mixes. And so the other thing we did is said, hey, we need to get this wet burlap on there. We need to get the deck soaked and keep it cured continuously for 14 days. We do that. The other thing we switched, we used to do manual kind of nail tining. We switched over to grinding the grooves in after the deck is cured. And then this is just a close-up of a typical grinding operation. So side-by-side comparison, the deck on the left, little or no cracks. The deck on the right was an older design with a recipe mix, about the 2-foot cracks on center. One thing we haven't figured out yet is the steel girder bridges still do have some cracks, even with our performance mix. So the next generation would be to add fibers. I think California and other states do that now. I think that's one thing that they help get rid of some of those additional cracks, even in the steel girders. So modified concrete overlays, this is our traditional preservation treatment on bridge decks. We have quite an inventory of those, over 585 bridges, about 14 million square feet. We're now in the second generation. So to use Microsoft's kind of vocabulary, we're up to Windows 10 in Microsoft. This would be, kind of deck overlay 2.0. And so if we get into that next generation, what do you do if a deck overlay has lasted 25, 30 years? How do you take it off? What do you do next? Those are the things we're getting into now. So this chart just kind of shows you a progression. We've used a lot of different varieties of recipe mixes, from latex to low slump to microsilica to fly ash. One thing we want to do is give the contractors lots of varieties. Also, the material supplies are always changing. You never know if you're going to have that material supply tomorrow. We used to have a great supply of Class F fly ash in our state, but the only coal burning plant is going out of business. So now Class F fly ash is kind of short supply, so microsilica is coming back into favor. And so the other difference is a lot of our contractors like to use ready-mix concrete instead of having the mobile mixer on site. And so then that's where the microsilica and the fly ash have the advantage, because it's ready mixed out of the plants. We've also now gone into a performance mix for our bridge deck. So the same performance mix I was talking about for a full depth bridge deck, we're using some of those in our second generations. So all these specifications are in our orange book this year, and it's in section 609. So it just talks about how we prep the deck. Generally, just like the previous presentation, we like hydromilling. And so we let the contractor choose between latex, microsilica, and fly ash. We're going to do hydromilling, and then we typically have a 42-hour cure. Now in the second generation, we're doing these performance mixes. So we would cure a normal deck for 14 days. We're trying to cure an overlay for just 7 days, and then do diamond grinding. So here's kind of a typical inventory of our modified concrete overlays and what the condition looks like. So about 4% are in poor condition based on our 2% patching criteria, and then about half are in fair condition and another portion are good. The thing is that we want to get 25 to 30 years. Over 187 bridges now have exceeded that 30-year life, and a lot of them are keeping on going. So the oldest one we have now is 39 years, and this is it. In Eastern Washington on Highway 2, this was a integral deck. At the time they experimented with it, it had about 10% deterioration patching. They put a latex modified concrete overlay on it. It's still doing really well, has very few little patches in it. And so this is a side view of the bridge. It's a concrete T-beam bridge with the deck integral in it. So at that time, they didn't have hydromilling, so they just rotomilled it and then jackhammered out the old deteriorated concrete. So here's a bridge up on I-90 if you're going westbound on I-90 heading back towards Seattle. This is called our Denny Creek Bridge. It's our first segmental post-tension box girder bridge built in the 1980. From day one, they put a latex modified concrete overlay to protect it. It just had normal reinforcing in it. So here's a kind of a cross section of it. One of the unique details that you need to know when you get in there to preserve it is it was designed with these big overhangs, and so it has post-tensioning transverse in the deck that's about 3.5 inches below the surface. So it's pretty important when you have maintenance on this or doing some repairs on that to know where those post-tensioning strands are, because it's not very easy to replace those if you had to. So here's a typical picture of this about 2016. Another thing that we found is on big bridges, our criteria doesn't really work. So we need to be a little bit more conservative on our criteria. So I looked at this bridge, the type of the bridge it didn't really meet our criteria, but I said, I'm really nervous about this. We need to get a preservation action going on in this one, even though it was only 1%. But if you look at the volume, it was 1,871 square feet of patching and spalls. And our maintenance crews were out there every summer doing repairs on this thing. So I said, okay, we need to get on this. So we got a preservation activity, got a contract going. So this last year, 2017, we did a hydromill. And here's the application of the concrete overlay going down. And then here's the curing. And then here's the deck. The deck looked pretty good. Did have some cracking in it, but so that was phase one. This summer we're going to get the third lane. We did 2 out of the 3 last year. We're going to do the third lane this year. So asphalt overlays. It's important part of our inventory. We have about 19% of our bridge decks, over 1,000 of them, have asphalt. They were even installed from day one, or they were installed afterwards. So as far as this paving train goes, this is the typical paving train you'd see on a roadway project. One of the things you need to know is a lot of this equipment is very heavy. So you have to pay attention to the load carrying capacity of your bridges. And then this material transfer vehicle is very heavy on 2 axles. So one of the things we did is we looked at the comparison of what this paving train looked like to the normal, even if we were to build a brand new bridge, HL93, and it's very heavy, 260,000 pounds compared to 164. So just to give you an example, Tacoma Narrows Bridge, our suspension bridge, we designed now a paving train that the contractors can use when they're repaving the bridge deck, so they know exactly what their limitations are on equipment. The rotomill. Rotomills are used for removing, lots of volume of asphalt on roadways, but they can do some damage on bridge decks. What we found over time is because of the tolerance and because of the operation and everything, they can go down and remove some of the concrete deck. They can actually remove chunks of rebar out of your bridge deck. So we set some limitations there on that. And so now if we have an integral bridge deck or some of our bigger bridge decks, we want to scrape off that asphalt instead of grinding. So here's a post-tensioned cable-stayed bridge in central Washington, one of the first ones in the United States. And it was from day one, it had an asphalt overlay put on it. Just a location map showing you where it is. And so here's, for years we just ground off the asphalt, put a new asphalt on it, back. But then we started saying, wait a minute, we can't tolerate this because we know we're doing some damage to the deck. This picture just kind of shows you how it was built in these segments. And so it's really important to know what type of bridge you have. So we let the contractor use this excavator, scrape off the asphalt on the bridge deck. We could see previously some damage from the rotomills. And then on this bridge deck, we put a membrane underneath the asphalt. So polyester overlays, we have 23 of those that we've done, and most of those are in good condition. So expected life about 25 years, and we're getting that. Downtown Seattle and I-5, one of our busiest spots. We did a polyester overlays about 11 years ago. It's still in good condition. This shows you kind of a picture where we had this Highway 18 It was originally just a 2-lane route. It got changed recently to a 4-lane route. So it's one of our first polyester overlays put down on a box girder bridge. It's starting to show some deterioration. We do have a progression there of how much deterioration is going on over time. And then recently, last year, we did another group of polyester overlays on Interstate 90 in eastern Washington. Those construction turned out really well. So the last one is the polymer overlays. And so we did a variety of those in the 90s and experimented with those, but with our studded tire use, they only have about a 5 to 7 year life, and then they start getting slick and lose their skid resistance. So now typically we use them on our movable bridges. So here's kind of a chart of where we do. We use epoxy coated rebar in all our bridges. Asphalt with membrane, if an existing bridge has one, we'll put it back on. One thing is when we take that asphalt off, we'll check out the deck. If it's deteriorated, we'll plan for it to have a concrete overlay in the future. Modified concrete overlays are our traditional system. Polyester overlays is when you need rapid construction. It's a good choice. And then polymer overlays for our movable bridges. So how do we measure success? One of the ways is look at how many bridge decks we've replaced in our history. In our entire history, we've only replaced 16 bridge decks, and some of that is because some of those were lightweight concrete and had some other issues on them. So that's pretty good success. So if you look and did just kind of this back of the napkin type of calculation, if you said, okay, if you look at all the bridges we put concrete overlays on, if half of those the decks had to be replaced, the difference in cost, we have saved about $1.2 billion over the last 35 years with our preservation program.
I'm just curious how well the latex modified concrete holds up to the studded tire wear.
One of the things I showed in that presentation, it depends on where you are in the state. In eastern Washington, where most of the people use studded tires, probably in about 20 years you can experience 1-inch ruts. The rest of the country, the rest of the part of the state, not so much.
Performance-based, it comes across to me as a mindset and close cooperation between suppliers, contractors, and yourselves. In other words, not just well, we'll just keep repeating doing the same thing over and over again. So can you talk just a little bit about that experience, how you transition, and what level of cooperation or communication you have with your suppliers and so on, like idea exchanging?
Well, anybody that's thinking about changing from like a recipe to a performance-based mix, you definitely have to engage your concrete suppliers community and talk to them about the criteria that you're going to be using so that they are aware of the tests that they're going to have to be running. But after they're up and running and you get that in that culture, it seems to work well. The contractors, the suppliers, everybody are on board now, so they're used to it.
Thank you very much, DeWayne.
Thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.